Consider the equation on the board. How can we prove that the series we are having at the left hand side is equal to the expression given at the right hand side? The best way to show this out is called mathematical induction, and that is the purpose of this video. And the basic idea behind it is to help us to show that an equation is true for some numbers of natural number or entirely for just natural numbers. So it involves 3 steps, which I'll be walking you through each and every one of these steps, one after the other, as we proceed forward. So without any further ado, let's get right into it. So the first step to show that this equation on the board is true is called the base test. And in this process, we want to substitute 1 for n and 2. However, you can use any other value like 3, 4, and so on. But the most often used, which is what I will highly recommend, is 1 and 2. That's enough. Keep in mind, you are familiar with sequence and series. Otherwise, you wouldn't be watching this video. N stands for the number of terms. So it means for n equals 1, we are considering the first term of the series at the left hand side. And the first term of this series at the left hand side is simply 1. So we want to show that 1 is equal to the entire expression we have at the right hand side when we substitute 1 for n again at that same side. So we have 1 over 2 times 1, which is n, times 1 plus 1, which is n plus 1. And if we simplify this expression, we have 1 over 2 times 1 times 1 plus 1 is 2. And finally, we got 1 to be equals to 1. So this makes sense. It means the equation is true when n equals 1. What about when n equals 2? What will happen? Well, at the left hand side that we're having the series, it means the first 2 terms of the series. Since it's a series, as you can clearly see, they are being added up. So we are taking 1 plus 2. And we must show that it is equal to 1 over 2, n is now 2. Instead of n, let's replace with 2 times 2 multiplied by 2 plus 1. At the left hand side, we have 1 plus 2, which is 3, equals 1 by 2 times 2 times 2 plus 1 is 3. And finally, again, we got 3 to be equals to 3. So since the first test has been passed, then you can proceed on the second step. Second step is called the inductive hypothesis. In this process, we want to assume that this equation will be true when n is equal to some number k. So this can go. So now, step 2, we want to consider or assume n is equal to k. And we want to assume that when n is equal to k, this stuff right here is also true. So let's try and substitute. At the left hand side, we now have 1 plus 2 plus dot 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 plus n is now k, you put k. Instead of n, you write k. Okay. So equals to 1/2 multiplied by k multiplied by k plus 1. And therefore we have 1 plus 2 plus dot 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 plus k to be equals to 1 over 2k times k plus 1. So this is what the equation becomes when n is equal to k. Now we want to use this as assumption and show that when n is equal to k plus 1, the equation is also true. Are we together? When n is equal to k plus 1, the equation is also true. This one is the assumption, this one is the proof. This n equals k is called the inductive hypothesis, trying to make the assumption, while this is called the inductive step or the inductive proof, trying to show that yes, your assumption is right. Perfect. So now, all we need to do is to plug in n equals k plus 1 as both sides. So for the left hand side that we have the series, we have 1 plus 2 plus dot 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 plus. Now it won't be k plus 1 that will follow immediately. We can't have k plus 1 when we have not gotten k. We said n is the number of terms. How can you get the second term when you don't have the first term? Obviously that. So it's impossible for you to have the k plus 1 term without having the k term. And don't forget, this doesn't mean the last term. It means the general term that provides everything in that series. Okay, so therefore we have the k term, and again plus the k plus 1 term. Okay, and this will be equals to 1 over 2. Now we're using this. Instead of n, we put k plus 1 times k plus 1, again times k plus 1, but we already have another plus 1 here, plus 1. Perfect. Right now, I need you to pay attention to this equation. Now we stated that 1 plus 2 plus dot 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 plus k is simply equals to 1/2 k times k plus 1. But it turns out to be present here. This entire series corresponds to what we have right here. Now, since what we have here turns out to be equal to this by the assumption we make, we are trying to use that assumption to show that yes, this one is right also. Then, can't we just say please? Instead of this, let's plug in this because they are equal. So therefore, we now have 1 over 2 k times k plus 1. Then we have plus k plus 1 here. Okay, don't forget it's only all the way from here to this point. Perfect. Then plus k plus 1 equals to 1 over 2 k plus 1. Oops. Then times k plus 2. So I've added these two ones. Okay, perfect. So now let's try to do some algebra. What we want to do now is that we want to ensure that the two expressions at each side is the same. So let's expand this. Let's expand this too. Now we have 1 over 2 k times k is k squared, and plus 1 over 2k times 1, that's just 1 over 2k. Then we have plus k plus 1 equals, let's expand this one first. We have 1 over 2 multiplied by k times k is k squared, right? Then k times 2 is 2k plus 2k. Then again, 1 times k is k plus k. And finally, we have 1 times 2, that's 2. So right now, we have 1 over 2k squared plus 1 over k plus k gives us 3 over k, or 3 over 2k to say. Then plus 1 to be equals to 1 over 2 times k squared plus 2k plus k, that's 3k plus 2. Perfect. And right now, for the left hand side, I think we have simplified enough. We can proceed more forward. So let's expand the right hand side. So we have 1 over 2k squared plus 1 over 2 times 3k, that's 3k over 2 plus 1 over 2 times 2. We find multiply with this, that's just 1. So I'll write this back. Is our result the same? What would you say? 3 over 2k plus 1. Well, notice that there's no difference between what we have at the left hand side compared to what we have at the right hand side. Then we can clearly say that since final conclusion, when n is equal to k and when n is equal to k plus 1, the equation is 2. Then, like you write the equation is 2, then the equation is 2 for all n equals natural numbers. That's a final conclusion. And that's how to easily use mathematical induction concept to show that an equation is 2. On to example number 2. Consider the equation on the board. Feel free to pause the video and figure this out yourself. Using the proof by induction, show that the equation is 2. So the first step is to consider when n is equal to 1 and when n is equal to 2. When n is 1, For the left hand side, it means the first term. And the first term of this series is just 1 times 2. So we have 1 times 2 to be equal to the right hand side is just an expression where we need to plug in the value of n to be equal to 1. So we have 1 by 3 times 1 times 1 plus 1 times 1 plus 2. So wherever you see n, you plug in whatever value you are trying to substitute. Perfect. So simplifying forward, 1 times 2 at the left hand side becomes 2. Then we have 1 over 3 times 1 gives us back 1 plus 1 is 2 times 1 plus 2 is 3. The 3 cancels out, and we have 2 to be equal to 2. So this one is passed. On to when n is equal to 2. For the left hand side, it means the first 2 terms. So that's going to be 1 plus 1 times 2 to say, then plus 2 times 3 to be equals to, so right now we plug in 2 for n right here. Then we have 1 over 3 times 2 multiplied by 2 plus 1, again multiplied by 2 plus 2. So at the left hand side we have 1 times 2 to be 2 plus 2 times 3 to be 6. And for the right hand side we have 1 over 3 times 2 plus 1 is 3 times 2 plus 2 is 4. So 2 plus 6 at the left hand side is 8. Okay, let me write it properly. Is 8 to be equals to 3 reduces 3, and the product of 2 and 4 is also 8. So it means the second test also passed. So the first stage is gone. Now on to the second stage, which is the inductive hypothesis. So we want to assume that the equation is 2 when n equals to some number k. Then we now use that to show that the equation is also 2 when n is equal to k plus 1, as long as it is 2 for n equals to k. So when n equals k, the equation becomes 1 times 2 plus 2 times 3 plus dot dot dot. So instead of n, we have k times k plus 1 to be equals to 1 over 3 k times k plus 1 times k plus 2. So all I've done so far is that I replaced n with k wherever I found n at both sides. Now that we have the next thing is to move to the third step, which is the last step. So we want to show that when n equals k plus 1, the equation is also 2. So when n equals k plus 1, for the left hand side, which we have the series, then we will have for k before for k plus 1. So we have 1 times 2 plus 2 times 3 plus dot 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 plus now for k, that's k times k plus 1. Now for k plus 1, we are referring to terms. Are we together? We're referring to terms, and k terms has to come before k plus 1 terms. That is why we are writing k terms. Are we together? Good. So k plus 1 terms now close. Now be paying attention to this one. Okay, n is now k plus 1, so we have k plus 1 in the bracket. Now we want to focus on the middle inside one. That's k plus 1 equals, now here we plug in k plus 1 as well. We have 1 over 3 times k plus 1. Would this please be enough? Again, times k plus 1 plus 1. I would plus 1 plus 1. Again, finally k plus 1 plus 2 right here. K plus 1 plus 2. Okay, perfect. I hope you are following. Now, just like what we did earlier in the previous example, as you can clearly see from our assumption, we said that this entire expression or series is equal to this thing right here. Now, since it turns out to show up over here, instead of writing it back, let's compress this to this. Therefore, we can now have it to be 1/3 times k plus 1 times k plus 2 plus, then we have this one left, k plus 1 times k plus 2. K plus 1 plus 1, that would be k plus 2. Perfect. This will be equal to 1/3 times k plus 1 times k plus 2 times k plus 3. Incredible. This is perfect. Okay, fine. So now, just like what we did earlier, so we want to try and just rearrange some things. So we need to expand. Okay, we need to expand so that we can have some like terms being added up. So we need more space, by the way. So at the left hand side, we have 1 over 3 times k. So let's expand the two binomials first. K times k, that's k squared. K be following k times 2, that's 2k plus 2k. Then k times 1 is k, I root x, plus k plus 2, which is 1 times 2. Then plus, let's expand the binomial again. Now, as you can clearly see, they are the same. So it means the expansion will also gives us the same result. So I'm writing it back again. That's k squared. Now, these are like terms, it will be compressed to 3k. Okay, so that I'm going to be repeating something many more times. Equals to, now instead of, let me get rid of this and just put 3k. Okay, that's just plus 3k. Perfect. Equals 1/3 of, now we expand something like that here. That's k plus 1 times k plus 2. And we have in a bracket k squared plus 3k plus 2 times k plus 3. Perfect. Right now, let's distribute this k into the bracket. Then we have 1/3. Okay, let's distribute everything, the 1/3 along with k. So we have 1/3 of k cubed plus 1/3, cancels the third and the 3 we have here. And we have just plus k squared. Then 1/3 of k times 2 gives us 2/3 of k. Okay, perfect. And we have plus k squared plus 3k plus 2 equals 2. Now we have 1/3. Now let's expand this again. K squared times k gives us k cubed. And k squared times 3 gives us plus 3k. Alright, then we'll do the same thing for this. 3k times k gives us plus 3k squared. And 3k times 3 gives us plus 9k. Okay, perfect. 2 times k gives us plus 2k plus 2k. And finally, 2 times 3 gives us 6. Then we have plus 6. Perfect. So right now we have 1/3 k cubed plus, now in the k squared, we have it to be 2 here. So it becomes 2k squared. Alright. Now 2/3 k plus 3k. What would that be? That would simply gives us 11 over 3k. So that gives us 11 over 3k. Okay, then we have plus 2 finally. So this becomes equals to, alright, 1 over 3 times k cubed. So we have 3k. Now this should be 3k squared because we have k squared times 3. That should be 3k squared. Okay, so we have 3k squared plus 3k squared, that's 6k squared plus 6k squared. Then plus 9k plus 2k, simply 11k plus 11k. Then we have minus 2 times 3, we got that to be 6. Okay, plus is a plus as well, plus 6. Perfect. And we'll close the bracket. So we are almost there. I think for the left hand side, no more simplification. We can move forward. We just have 1/3 of k cubed plus 2k squared plus 11 over 3k plus 2 to be equal to, now let's distribute the 1/3 here. We have 1/3 of k cubed plus the third, reduce the 6 to 2, and we have 2k squared, and the third, reduce this one to 2 as well, but it can't reduce the 11. Then we have plus 11k over 3 plus 2. Now are they the same? Absolutely. So therefore, since the equation is 2 for n equals to k plus 1, then it is also 2 for n equals to k. And therefore, it implies that it should be 2 for all n equals natural number. So this is how to easily use mathematical induction to prove that a certain equation is true or not. Now for easy understanding, let's consider one more example. But I want you to pause the video and figure this example out yourself. On to example number 3. Consider the series on the board. Prove that the equation is 2 for both the left and the right hand side. So just like before, we start by showing that the equation is 2 when n is equal to 1 and when n is equal to 2. So when n is 1 for the left hand side, which we have the series, that refers to the first term, and that's simply 1 squared. So for the right hand side, we have the expression 1/6 times 1 times 1 plus 1 times 2 times 1 plus 1. So what I've done so far is that I plugged in 1 as n everywhere I see n at the right hand side, and that's it. So now we have 1 to be equal to 1/6 times 1, which is 1. We don't need to write that again. Then we just have 1 plus 1 in the bracket, 2 again, times 2 times 1 is 2 plus 1, that's 3. Now these entirely cancel the 6, and we have 1 to be equal to 1. So this passed. The next one is when n is 2, where we have the 6 at the left hand side. We are considering the first two terms, which we have right here to be 1 squared plus 2 squared. And for the right hand side, we plug in 2 for the value of n. So we have 1/6 times 2 plus 1 times 2 times 2 plus 1. And for the left hand side, we have 1 plus 2 squared is 4. And we have 1/6 times 2. 2 plus 1 is 3 times 3. Again, times 2 times 2 is 4 plus 1 is 5. So 1 plus 4 is 5 right here. And 2 times 3 cancels out 6. And we have 5 to be equal to 5. So it means the equation is 2 for n equals 1 and n equals 2. And therefore, the first case is passed. On to the second case, which is the inductive hypothesis. Now I want to assume that n is 2 for a number k. Now we now use this to show that it is also 2 for n equals k plus 1. So once we can show that it's 2 for n equals k plus 1, then we'll now make a conclusion that since it is equal to, since it is 2 when n is equals k plus 1, then it is 2 when n is equal to k. And then we have it to be 2 for all natural numbers. So now, when n equals k, all we need to do is to plug in k wherever we see n. So we have 1 squared plus 2 squared plus ... plus k squared at the left hand side to be equal to 1/6 k times k plus 1 times 2k plus 1. So that's our expression for n equals k. Now on to the inductive steps, which involve showing that it is 2 when n equals k plus 1. So when n equals k plus 1, the series we have at the left hand side becomes 1 squared plus 2 squared plus ... plus k squared plus, now we have for the k plus 1 term, that's k plus 1 all squared. Perfect. And this will be equal to 1/6. Now we have n right here, so instead we put k plus 1. Alright, then we have n plus 1 right here, it becomes k plus 1 plus 1. Again, we have 2n plus 1, that's 2 times k plus 1 plus 1. Perfect. So as we have been making the substitution so far, this right here is the same thing as what we see here. So instead of that, let's put 1/6 k times k plus 1 times 2k plus 1. And we have plus k plus 1 squared. Perfect. Equals 1/6 times k plus 1 times this k plus 1 plus 1, that's k plus 2. Again, times 2 times k is 2k plus 2 times 1 is 2 plus 1 that we have here. So what I've done is that I expanded this bracket with the 2. So the 2 will be distributed. We have 2k plus 2. Now this plus 1 is there already, and that's how we have it there. I hope you're following. Perfect. So now let's try and do the algebra. So let's expand right now. So we have 1/6 k times, so k times 2k, that's 2k squared. 2k squared. K times k gives us k plus k. Then 1 times 2k gives us plus 2k. Then 1 times 1 gives us plus 1. Then we have plus k plus 1 squared. We can also expand that. Alright, becomes k plus 1 times k plus 1. Let me split it first. This is equal to 1/6 of k plus 1 times k plus 2. Now this becomes 2k plus 3. 2k plus 3. Incredible. Okay. Now we have 2k here. Then I added this 2 and 1. Perfect. So now we have 1/6 of k times 2k squared. And these are addable. We have 3k plus 1 plus, now let's expand this one as well. That becomes k times k is k squared plus 2k plus 1. Alright, so k times 1 is k, 1 times k is k, added up 2k. Perfect. Then we have 1 times 1 to be equal to 1. This is equal to 1/6 times, let's expand this one, k times k is k squared. I think we expanded something similar earlier. At the middle, we have plus 3k. And finally, we have plus 2. Then we have to multiply 2k plus 3. Perfect. So now let's distribute the 1/6 inside this one. Then we have 1/6. Okay, the 2 reduces to 1/3. So we have 1/3 of k cubed. Alright, the 3 reduces this one, the 6 to 2. Then we have plus 1/2 of k squared. And finally, we have 1/6 of k. Then we have plus k squared plus 2k plus 1 equals 1/6 times k squared times 2k gives us 2k cubed. Okay, perfect. K squared times 3 gives us plus 3k squared. Okay, then 3k times 2k gives us plus 6k squared. We have plus 6k squared. Then 3k times 2 gives us plus 9k. Plus 9k, that's 3k times 3. 2 times 2k gives us plus 4k. And finally, 2 times 3 gives us 6. Plus 6. Okay, perfect. So now, let's get rid of this one. Then we have 1/3 of k cubed plus 1/2 k squared plus k squared gives us 3/2 k squared. That's 3/2k squared. Okay, perfect. Now 1/6k plus 2k, that will give us about 13/6k. Then we have plus 1 as a constant equals to 1/6 multiplied by 2k cubed plus 3k squared plus 6k squared. That's 9k squared. Right? Then we have 9k plus 4k. That's 13k. 13k. Then we have plus 6. Perfect. Now the left hand side is gone. We can't simplify more forward, so we just need to repeat it one more time. Plus 3/2k squared plus 13/6k plus 1 equals to, upon distributing the 1/6 here, the 2 reduces the 6 to 1/3 k cubed. Perfect. Plus, what about when 1/6 is multiplied by 9 squared, 9k squared, we have now with 3/2k squared, because 3 here 2, 3 here 3. Plus, now this can be reduced, we have 13k/6 plus the 6 reduces the 6 to 1. So are they the same? Absolutely. So that's it. Now we have shown that the equation is 2 when n equals k plus 1, and this will make it to also be true when n equals k, because it is the one we use to show that it is true when n equals k plus 1. And that's it. We can make a final conclusion that the equation is true for all natural numbers. This is how to easily use the concept of mathematical induction to show or prove that an equation is true. I hope you find this helpful and understandable. Thanks for watching. See you in the next video. Bye for now.